In this video, I will explain about thermal resistance network. Consider steady one-dimensional heat transfer through a plane wall of thickness L, area A and thermal conductivity K exposed to convection on both sides to fluids at temperatures T infinity 1 and T infinity 2 with heat transfer coefficients H infinity 1 and H infinity 2 respectively, assuming T infinity 2 is lower than T infinity 1. Note that the temperature varies linearly in the wall and asymptotically approaches T1 and T2 in the fluids as we move away from the wall. Under a steady condition, the energy balance on the wall is illustrated here. The rate of heat convection into the wall equals the rate of heat conduction through the wall equals the rate of heat convection from the wall. In a symbolic form, it can be expressed as in equation 313. By rearranging equation 313, we can simplify the expression as demonstrated. This simplified equation can be expressed in terms of thermal resistance as illustrated in equation 314. By adding the numerators and denominators of equation 314 yields equation 315. R subscript's total is the total thermal resistance between two locations with the different locations' temperatures. It is sometimes convenient to express heat transfer through a medium analogously to Newton's law of cooling, as shown in equation 318. Capital U is the overall heat transfer coefficient with the unit watt per square meters Kelvin. A comparison of equations 315 and 318 revealed that the product of overall heat transfer U and surface area A is inversely proportional to the total thermal resistance as described in equation 319. Consider a plane wall that consists of two layers, such as a brick wall with a layer of insulation. This type of wall is known as a composite wall. The thermal resistance concept can determine the rate of steady heat transfer through composite walls. This is done by simply noting that the conduction resistance of each wall is L over Ka, connected in series and using the electrical analogy. By dividing the temperature difference between two surfaces at known temperatures by the total thermal resistance. The rate of steady heat transfer through this two-layer composite wall can be expressed in equation 321. The R total is the total thermal resistance as shown in equation 322. Consider a two-layer plane wall subjected to convection on both sides. The subscripts 1 and 2 indicate the first and the second layers respectively. We could also obtain this result by following the approach already used for the single layer case. Noting that the steady heat transfer rate through a multi-layer medium is constant. Thus, the total thermal resistance is simply the arithmetic sum of the individual thermal resistances in the heat transfer path. This result can be extended to plane walls consisting of 3 or more layers by adding an additional resistance for each layer. The thermal resistance concept is widely used in practice because it is intuitively easy to understand. It has proven to be a powerful tool in solving a wide range of heat transfer problems. but its use is limited to systems involving steady heat transfer with no heat generation, such as resistance heating or chemical reactions within the medium.